In telecommunication, bipolar encoding is a type of return to zero (RZ) line code, where 2 and 0 values are used, so that the three values are plus, dash, and 0. Such a signal is called a duobinary signal. Standard bipolar encodings are designed to be DC balanced, spending equal amounts of time in the plus and states. The reason why bipolar encoding is classified as a return to zero (RZ) is because when a bipolar encoded channel is idle, the line is held at a constant zero level. And when it is transmitting bits, the line is either in a plus V or V state corresponding to the binary bit being transmitted. Thus, the line always returns to the zero level to denote optionally a separation of bits or to denote idleness of the line. One kind of bipolar encoding is a paired disparity code, of which the simplest example is alternate mark inversion. In this code, a binary 0 is encoded as 0 volts, as in unipolar encoding, whereas a binary 1 is encoded alternately as a positive voltage or a negative voltage. The name arose because, in the context of a T-carrier, a binary single quote 1 single quote is referred to as a mark, while a binary single quote 0 single quote is called a space. The use of a bipolar code prevents a significant buildup of DC, as the positive and negative pulses average to 0 volts. Little or no DC component is considered an advantage, because the cable may then be used for longer distances and to carry power for intermediate equipment such as line repeaters. The DC component can be easily and cheaply removed before the signal reaches the decoding circuitry. Bipolar encoding is preferable to non-return to zero whenever signal transitions are required to maintain synchronization between the transmitter and receiver. Other systems must synchronize using some form of out-of-band communication, or add frame synchronization sequences that don't carry data to the signal. These alternative approaches require either an additional transmission medium for the clock signal or a loss of performance due to overhead, respectively. A bipolar encoding is an often good compromise. Runs of ones will not cause a lack of transitions. However, long sequences of zeros remain an issue. Long sequences of 0 bits result in no transitions and a loss of synchronization. Where frequent transitions are a requirement, a self-clocking encoding such as return to zero or some other more complicated line code may be more appropriate, though they introduce significant overhead. The coding was used extensively in first-generation PCM networks, and is still commonly seen on older multiplexing equipment today, but successful transmission relies on no long runs of zeros being present. No more than 15 consecutive zeros should ever be sent to ensure synchronization. There are two popular ways to ensure that no more than 15 consecutive zeros are ever sent: robbed bit signaling and bit stuffing. T-carrier uses robbed bit signaling. The least significant bit of the byte is simply forced to a 1 when necessary. The modification of bit 7 causes a change to voice that is undetectable by the human ear, but it is an unacceptable corruption of a data stream. Data channels are required to use some other form of pulse stuffing, such as always setting bit 8 to single quote 1 single quote, in order to maintain a sufficient density of ones. Of course, this lowers the effective data throughput to 56 kilobits/s per channel. If the characteristics of the input data do not follow the pattern that every 8th bit is single quote 1 single quote, the coder using alternate mark inversion adds a single quote 1 single quote after 7 consecutive zeros to maintain synchronization. On the decoder side, this extra single quote 1 single quote added by the coder is removed, recreating the correct data. Using this method, the data sent between the coder and the decoder is longer than the original data by less than 1% on average. Another benefit of bipolar encoding compared to unipolar is error detection. In the T-carrier example, the bipolar signals are regenerated at regular intervals so that signals diminished by distance are not just amplified, but detected and recreated anew. Weakened signals corrupted by noise could cause errors, a mark interpreted as 0, or 0 as positive or negative mark. Every single bit error results in a violation of the bipolar rule. Each such bipolar violation, BPV, is an indication of a transmission error. The location of BPV is not necessarily the location of the original error. For data channels, in order to avoid the need of always setting bit 8 to 1, as described above, other T1 encoding schemes, modified OMI codes, ensure regular transitions regardless of the data being carried. In this way, data throughput of 64 kilobits/s per channel is achieved. B8ZS is a newer format for North America, where HDB3 is the original line coding type used in Europe and Japan. A very similar encoding scheme, with the logical positions reversed, is also used and is often referred to as pseudo-ternary encoding. This encoding is otherwise identical,